So let's consider the equation lambda associated with this operator and see how we actually get this complex, how we go through the complex analysis to get these answers. Right, here's a complex method, and we turn this operator expression into lambda expression, where lambda here is a complex numbers, right? Possibly involves imaginary numbers. So if you solve this thing for lambda, and then of course it factors through, just completed the square part like this, and the lambda is going to be a and plus minus bi, right? So using these two solutions, if b is not equal to 0, and we consider, I'm going to call C1 bar for complex coefficient, and with this coefficient here, a plus bix there, and plus C2 complex coefficient, because we enter complex functions. So if you extend the world of functions to complex, and if you look at it here and formally just integrate and differentiate this e to the something, when we're treating this a minus bi as just a constant here, then it'll satisfy this equation. And after you go through this derivative and treating this a plus bi, a minus bi constant, it's going to be 0. But what we're interested in here is real valued function. So you have to just sort it out. It's a real valued function. You have to sort it out which part is a real part and which part is an imaginary part in here. So I wrote it up there. So simply I'm going to write the C1 bar as a C1 and C2i complex numbers, and use this Euler's formula or polar form to rewrite this one in terms of sine and cosine. Here the real part is ax, so it picks up e to the ax, and I imaginary part is a bx, so that becomes cosine bx plus I times the sine bx. So that's what this part is. If you look at the second term, I'm going to write using C3 and C4 I, that's what this C2 bar as a complex number is. Then we pick up the same real part ax, so we're going to go e to the ax, and this negative bix, and bx is real part multiplied to the imaginary I, so we have cosine of negative bx plus I times the sine negative bx. So that's all the real part and imaginary part separated like this. And what we want is, amongst all these functions in here, which part is a real part of the function, so that we can pick up solutions for the real valued functions. So this is the sum of a real part and imaginary part. This is sum of real part and imaginary part. To simplify, it's a real part here. It's in blue color, so you multiply. You can see that these two multiply gives you a real part. And if you multiply cross in it here with I, it's not going to be real, so you have to multiply I and I. So what I see here is a e to the ax and C1 cosine bx. So that's if you multiply it here. And if you multiply these two, we get I squared and negative, so it's negative C2 e to the ax, sorry about the different order, but we have sine bx picked up. Now if you look at the second line, we have C3 and multiply to the e to the ax. Since cosine is odd even function, so cosine of negative bx is the same as cosine of bx. So here's a cosine bx. If you multiply this I and I, that's negative, but this is an odd function. Negative makes it positive, so I think here it's a C4 e to the ax sine bx. I think that's it. That's the entire real part. So I moved it up there. Well, we're not interested in imaginary part, so I'm just going to plot it here. Everything else will have I part in there, and blah, 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 whatever, that is not going to be something we'll be interested in. This is the part we're interested in. So from there, we have a real valued function pop out. Real valued functions. From this complex trig is that e to the ax and cosine bx and e to the ax and cosine bx. So let's collect that. What's in front of e to the ax, cosine bx, is this c1 plus c3, I think. That's the real number. And what's in front of e to the ax, sine bx, is we have c4 and we have c2 in there, right? All right, so you can collect that. So the bottom line is that what it's saying to us is possibility of the real valued functions are generated by this function e to the ax cosine bx, and another generator is e to the x and sine bx. If you think about it, when we pick out this e to these two generators in polar form, we assume that there is not a repeated factor. So we've been using this b not equal to 0 all along, actually. So here we recover the e to the ax cosine bx and e to the ax sine bx. Not too crazy. It's just this reasonable calculation. If you compare it with the tricky organization I have to pull out with the sine tangent bx and a cotangent bx, this is better. Of course, this is a slick way of doing it, but it doesn't really constitute a proof or anything. So there's this advantage and disadvantage. So let me adjust it. So one last summary here is that if you have that operator in second order, if it factors with a positive coefficient outside the perfect square, and it factors over the real like this in two different factorization, and from there naturally the sine bx and cosine bx shows up. So if you look at the kernel of this one, and we have this solution eax cosine bx, if you look at the other part, we have eax and sine bx. So if b is not equal to 0, we can put it nicely. There's these two things from each kernel gives you the full solution of the kernel of the second order. But if you look at the complex method, that you turn that quadratic equation to a quadratic equation of complex numbers, then if you compute the solution, you have a plus bi and a minus bi. So once you have that, this a appeared as e to the ax, part of the solution. B goes inside the sine and cosine part, becomes cosine bx and sine bx. So you can kind of play with a complex number and arrive in the same conclusion, although it's not a proof.